SEEE4433 is for power electronics and drive. What is the content of this course? So if you look at here, is it clear?
Yes, doctor.
Okay, so you can read it clearly here. The course synopsis here says that this course introduced to the fundamentals of power electronics, including what? Power converters, like rectifier, chopper, inverter, and all of those power converters requires you to use the switches, and switches are actually made from semiconductors. Okay, also in this course we're going to see some operations and analysis for the converters that we're going to look at. Yeah, there are three converters here: rectifier, choppers, and inverters. In terms of what? Steady state operation. Yes, only steady state operation. Why do we say that steady state operations? Because we also have dynamic operation. Dynamic operation refers to the transients as startup. Okay, that is more complicated because it's not steady state yet. But then in this course, we're only focusing on the steady state when it becomes stable. So it's much easier. So this course also exposes you guys to some basic, basic, fundamental, basic converters designed, and the selection of the suitable converters for certain applications. Okay, so once you know the behavior or the nature characteristic of the converters, so you should be able to apply in the daily applications, in your designs. So which converters actually you can use for what kind of application, right? To suit and also to match. So finally, what do you do? Okay, covers the operation and selection of converters, the same thing, I guess. So at the end of the course, a student should be able to critically design, given some specifications, using application of software. Most probably you'll be using the software name MATLAB Simulink. So it's not a new thing because you have taken the subject before. You'll be doing assignment on the design of power converters using MATLAB Simulink. Okay, and then in the exam and test also you'll be exposed to some calculation of design as well, with some specification given. So there will be mathematical analysis and calculation. Theory as well. So basically that is the overall of the content of the course, yeah? And let's see what is expected at the end of the course. So we have the CLO. Anyone knows what is CLO here?
Course learning outcome.
The course learning outcome. Why do we have CLO? Because we need to comply with OBE. Okay, OBE stands for outcome-based education. Okay, that's the 21st century educational learning method, I guess. So CLO is the course learning outcome. In this course, we have two. What is number one? To solve problem related to steady state. Again, emphasize here only steady state operation of power electronic converters, circuit and motor drives. Okay, there are two things. One is static, another one is drive. So I'll explain to you later in this chapter 1 what is drive and what is static converters. So this one will be mapped to PLO3. PLO stands for Program Learning Outcome. Yeah, program is for SKEE. Course Learning Outcome is SKEE 4433. And program refers to your electrical program, SKEE. That lasts for 4 years. This is only one course. What is the second course learning outcome? Design power converters based on the given specification. So basically CRO2 will be mapped on your assignment. Yeah? And there's one question on the final exam. Okay. one question number 2, I guess, Q2. Totally on design, but not difficult, is it? So CRO1 will be met on your test, quiz, final exam as well. Okay, so what is the teaching and learning method that we should use? Okay, in short, we'll just say it as an active learning method, active learning method. Okay, the course coordinator for SKE4433 is Dr. Shireen, yeah? Course learning method, we are using active learning. Project-based learning is for your assignment. Oh, it's given here, instruction. Student will be divided into a group consisted of 2 or 3, or 2 or 3 students. Okay, so maximum 3 students in a group. You can form your groups from today to do the assignment. Yeah, assignment will be given later, but you can form your group first. So let's go and see what is the assessment. We will be having quizzes from time to time. It says here 1 to 4. So the percentage of contribution to the course will be 5%. So I think I will do it 5, so that 1% for one quiz, maybe. Not sure. The more the merrier. Okay. But tests, we have 2. Test 1 and test 2. Okay, we have 2 tests. One test contribute for 15%. So total you have 30%. So assignment based 15%, this assignment, most probably we have 2 assignments, okay, half-half. Final exam as usual, you will be having Q1 to Q4, which you have to answer all. Okay, in the final exam, 4 questions. So one question would be 12.5 marks. Altogether, you have 50%. Okay, that is just the mapping of PLO3 and PLO4, 40%, 10%, total 50%. So that is the 100% of assessment for your SKE 4433. Okay, depends on how much do you want to collect from here, yeah? So what else? Okay, the textbook, if you can find this, will be a good reference for your learning. So this course outline, basically, I've already uploaded on e-learning. You can get it and refer it back if you miss anything. Okay, let's go through quickly on what are the content in the weekly schedule. So basically, chapter 1, we have 2 weeks to do it. So this week and next week, we'll look at what the fundamental concept of power electronics and application, definitions, examples, and where do you use it. And then you will look at the power devices, and there are actually many of the power converters, and the different converters will be using different semiconductors or power devices. Basically, when we say power devices, it's actually referring to switch. What is the function of switch? On and off, that's all. So switching and related issues, right, is not ideal. So in practical, you have all these considerations. We'll look at it later. So for chapter 2, for how many weeks? Oh, seems to be very long. Where is chapter 2 finishing? Okay, chapter 2 is a lot. Oh, here, chapter 2 is 1, 2, 3, 4 weeks. A very long chapter. AC-DC converters, which is also known as rectifier, changing from AC to DC, covers half-wave rectifier, and then different loads, RL, and DC source. And then we're going to continue with the full wave, half wave, and then full wave. Same thing, repeating the different loads. And then where do you apply this rectifier? Here comes the drive, okay? Rectifier plus the application of drives, and then you have DC motor drives here. And then after you finish everything, then you're going to sit for your test 1. When is the test 1? I think this is just the tentative, yeah, tentative, just proposing. Okay, we'll finalize this one later. But then somewhere in mid-April to end of April, yeah? Okay. Most probably at night time, because we also have part-time students in KL, I guess, yeah. So it will be done online. Good thing, isn't it, online? But final exam, you will have to come back here, yeah? Okay, are we going to include everything in test one? No, we only stop here. So test one will be covering until week 1 to week 3. Okay, test one will cover until half-wave single-phase rectifier. So you have time on week 4 to study, week 5 to study, week 6 you sit for the, maybe week 6, yeah, 6 for the test. And then you come to the week 7, have a good break. And we will continue with chapter 2, right? So it will be chapter 3. Chapter 3 is DC-DC, or is known as chopper. How many weeks? Oh, that's a lot. 3 weeks as well. Chapter 3, so we will look at 3 things only. One is buck, the second is boost, the third will be buck boost. 3 major group of this chopper, DC-DC converter. And then some brief summary on isolated and non-isolated converters, not into the details. Okay, and then application, how do you apply these DC-DC converters in a drive, yeah? Drives that involves motor and the speed control. Then finally, I guess, would be the inverter from week 11 to week 14. Okay, inverter. Inverter, we will cover square wave inverter, basic. So when we talk about inverter, DC to AC converters, you will be dealing with harmonics. And then we need to calculate the THD, which is the total harmonics distortions. And we have single phase and 3-phase inverters. Then it comes to different types of the inverter, quasi square wave. And then finally, we have bipolar PWM, which stands for pulse width modulation, single phase and 3-phase inverters. So all the inverters you will have to deal with this calculation, yeah, THD calculation. And then again, for each of the chapter, you notice that we're going to continue or end the chapter with the application of drives. Okay. So same thing goes to the last chapter, inverter. You will have the drive application as well. Okay. Any questions so far for the course information? That's the overview of what you're going to go through for the whole semester. 4433. Anyone? Any question?
Excuse me, Prof.
Yes.
For test 2, what will be covered for test 2?
Oh yeah, test 2. Yeah, I missed out
Yeah.
test 2. Where's test 2? Test 2. It's not. Oh yeah, it's written here. Test 2. Basically, test 2 is on DC-DC plus inverter. Beginning of inverter. Because you have finished chapter 3 already, DC-DC, and then inverter beginning, I think it will stop here until quasi square wave. So that is the content of DC-DC test 2. Yeah. Mid-June, that will be somewhere mid-June. Mid of June. Exact date maybe will change later, not sure. Okay, so test 1 and test 2 will be online. Then I forgot to mention that final exam will be face-to-face. Yeah, you guys know, right? There's a memo that given by SKE, or the final exam will be done face-to-face. So if you like it or not, you have to come back to UTM before the final exam. Okay, because I see that more than half of the class here still staying at hometown at the moment. So you can still enjoy your holiday or vacation at home until the end of the semester, and then come back here for the final assessment. Any more questions regarding this course information? Nope. All right, let's begin our lecture. I think nope. You need a break? Okay, 5 seconds. Okay, done. Okay, if you notice that according to the lecture notes, right? For chapter 1, I basically have 4 files. Yeah? Chapter 1 will be split into 4 files. So today we're going to continue with the first file, which is the introduction to power electronics. So let's begin. What is power electronics? So power electronics, you see that the word itself or the name itself saying that you have power as well as you have electronics. So what is that? Is it power or electronics? It's actually ranging from electronics to big power system. Okay, very, very large and wide area. So what is electronics here? It says that electronics, the solid state electronic devices and their driving circuit. Anyone knows what is solid state? You've been hearing all these terms long ago, yeah? When you buy your laptop, you buy your extended drive, you want to buy solid state drive, right? So what is actually solid state? Anyone knows? So quiet. Anyone here? Tesla?
Yes, doctor.
Your name is Tesla, is it?
Yeah, that's my English name.
Wow. You know Elon Musk, your brother.
Maybe.
Okay. What is solid state?
I think maybe their state, the state of the electronic device is stable, solid, not change. They are obviously that they have certain states according to their I don't know how to describe it.
Okay. You're not
Yeah,
local, is it? Where you from?
I come from China.
I see. So
Yeah,
Tesla Yang, you're not Malaysian, you are from China. So we have from China, from Indonesia, any more overseas students? 2 only in this class. Okay, so to answer what is a solid state, it's given here. Can you read it in the green one?
sure. Solid state is a common descriptor used to refer to electronic components, devices, and systems based entirely on semiconductor materials such as silicon, uh, germanium, or gallium arsenide.
Yes, thank you. So solid state, it refers to semiconductors, right? Devices that are entirely based on semiconductors. You guys have learned about silicon, germanium, and today it's widely used, the new thing, which is the gallium arsenide as well, silicon carbide, etc. So new semiconductors evolve to replace the conventional silicon and germanium. So solid state electronics, which is things that related to semiconductors, and their driving circuits. Driving circuits here means what? You drive your car? No, it doesn't mean that. Yeah, this drive circuit is not driving your car. It's actually to drive the circuit. Yeah. Okay, we look at the definition later on what is a drive circuits. So electronics, power. What is power? Static and dynamic requirements of generation, conversion, and transmission of power. Static means no movement. Dynamic means it will be some changes. Basically, it's from start to steady state. Okay, dynamic. Start means what? 0. Nothing happened. So when you turn on the supply and then become going on up and rising gradually or exponentially, we're not sure, until it becomes steady state. So from 0 until the steady state, that will be dynamic. If you would like to draw a graph, so the from 0 will be here, isn't it? You're starting the time. So the behavior could be rising from like this until it becomes steady state. So this point is steady state. So from 0 until steady state will be known as transients. And that we call it the dynamic change. Okay, dynamic is referring to the transient state. That will be the steady state on the right hand side. Can you see my drawing?
Yes.
Okay, good. And then control. What is control? The steady state and dynamic stability of the closed looped system. You need to do control. When you enter a room, right, you want to turn on the light. What do? You turn on the switch. That is a control. Directly control on and off. But sometimes when we requires the output or the result to be slightly complicated, so you need to give a better control signal. If you look at diagram at the bottom here, at the bottom arrows here, you see that that's like a control signal. Okay, we as the user will be given, we will give the signal to the device, whether you want it to become whatever. So you can set your control signal, or sometimes we call it as the feedback signal. Okay, you want to set it, for example, the output power to be constant, 5 volt. Okay, you want to make it 5 volt all the time, no matter what changes here. Okay, it may be changing, but I want the output to be 5 volt constant. So the feedback will be doing the operation, plus minus, compensation, etc. Okay, so the output will maintain 5 volts all the times, regardless of what happened in the input. So input may be changing, yeah? For example, if you're putting a solar panel here, we know that solar panel actually depends on the sunlight. So if the sunlight is very good, then your output will be, the output, which is the input to the power, electric power here, will be high. But if the sun is falling or setting, then the output of the PV panel will be reducing. So it will become getting down, isn't it? The output and the input to the conversion will be low. Okay, so the control signal will be doing the work to make sure that the output is always 5 volt. So regardless of what happened in the input side, the output is always maintained at 5 volt. So that is known as control. So who is doing the control basically in today's, right? We are using everything digitalized. Okay, we are using processors, digital power, DSP, we call it digital, as a digital signal processors. Okay, so everything digitalized. Okay, so what is power electronics? Power electronics basically referring to anything that dealing with electronics to the scale of power systems that involve control. Okay, so this diagram at the bottom will give you the brief idea of what is power electronics. It will do the work of control plus, there's a word here, control plus conversion of power. What do you mean by conversion of power? You can do the conversion of power. And sometimes we call it energy conversion. Okay, let me ask you, output from the PV is DC or AC?
DC, Doctor.
DC. This 5 volt is DC or AC?
AC maybe.
5 volt or
DC too.
DC. USB. USB uses 5 volts. So DC is a form of electricity, correct? What is electricity? Electricity can be in DC and AC. So what is electricity? Electricity belongs to energy. Energy conversion. So I'm changing from DC to DC. Did I change anything?
No.
Input is DC, output is DC. So did I change anything? No. But did I do energy conversion?
Yes.
The form of energy is still the same, but energy conversion happens. Why? Because the input is not constant, isn't it? But output is constant. So for DC to DC, if you do this kind of control, normally we call it as regulation. I'm regulating the output, DC regulation, yeah, regulating the output voltage to become a constant. So this is called the conversion of electric power. So how to do it? You were going to use power electronic converters, right? So that is the definition for power electronics. Let's see the further definition here. Power electronics actually is application of solid state electronics for control and conversion of power. So make sure that you key in these two keywords when defining power electronics. What is power electronics? You must have the keywords of control and conversion of energy or power. If this either one is missing, then it's not power electronics. Okay, convert or process and control the flow of electric power by supplying voltage and currents in a form that is optimally suited for user loads. Okay, it's not necessary to be voltage and current all the time. And sometimes you only control the voltage, sometimes you only control the current. And in some application, you control both the current and voltage. Okay, depends on what application or design that you are dealing with. So either way, they are all under this diagram. You control the signals. Of course, when you do this control signals requires what? Input, isn't it? So you will need to have sensors to sense the current, for example, or to sense the voltage on the output side. And sometimes you will need to send the current on the input side or the voltage on the input side. And then this control signal, basically, I will call it as a calculator. It will calculate based on your requirement and send the signals to the converter. This green color box or blue color box is actually the power converters that having the solid state devices, which is the switch. Okay. This switch will be doing on and off job based on the control signal. And then to achieve the output that you want. So that is power electronics. Okay, next. Another one example of simplified block diagram for power electronic system. If you notice this diagram, you only have one single input here and one single output. Okay, same things. You have controller that come receiving the feedbacks and also the references that you set to achieve the certain objective of the electric output power. Is it possible that we expand these power converters to receive multiple inputs and also to have multiple outputs? Just now I said example, I only need 5 volts output, right? In this case, I need 5 volt, 9 volt, and 12 volts. Is it possible? Yeah, it is possible. So you can go for multiple inputs. Here representation is given by x1, x2 to x number, xm number. And then you also can set your output to become multiple. You can have 5 volts, for example, 9 volts, 12 volts. I'm talking about DC application here. So then the feedback signals will be doing different jobs. Okay, you will have a different partition, for example, to control the Y1, Y2, Y3 until YM. Okay, because processor, it just depends on the memory as well as the size, the RAM inside. Okay, if it is managed, is able to do the operation of calculation, then it's fine. It regardless of how many outputs or inputs you want. And then the output is not necessary in terms of electrical. Yeah, it could be mechanical loads. Okay, for example, if you want to control the motor is spinning, right? So it's mechanical, kinetics. So anything. So bear in mind that power electronics can be done to receive a single inputs and controlling single outputs, as well as multiple inputs and multiple outputs with multiple control signals. It can be done. This one is an example of electrical mechanical system dealing with power electronic circuits. Do you notice where is power electronics here? Okay, the power electronics is in this box. PE stands for power electronic circuits. So it will talk about the left-hand side here, form of electrical energy inputs. Inputs is going through the first box here known as filter and rectify. Okay, mostly AC lines voltage, single or three-phase. Okay, input from the transmission line maybe. Okay, so the pre-stage here is doing the filter. What is filtering doing? Filter out the noise, harmonics. Okay, and rectify is actually changing from AC to DC. Rectification. Okay, so our input is AC, then it goes through the pre-state of these rectifications is changing from AC. AC we know that is sine wave, going to DC. DC will be a steady state voltage, and then it will go inside the power processing stage here, power PE, power electronic circuits. So what is this function of this box? It's doing, not mentioned here. But if this is already DC, then the output will be DC as well, right? Is it? I'm not sure. It doesn't say anything here. Assuming it's DC, for example. So if this is DC and DC, the box will be chopper. DC-DC converters. But in the case that I don't want it to be output DC, I want it to be output AC. So what is the name of the converter here? From DC to AC, it's known as inverter. If DC to DC is chopper, DC to AC is inverter. So it could be two possibilities here. So the control circuit will be doing the work of processing the feedback signals and decide on how to control. Yeah? Basically, the control will be setting the time of on and off. Well, how long you want to turn on and how long you want to turn off. Okay, for what? For the switch, which is the solid state devices. Okay, the switch will be controlled by the control circuit on how long it turn on and how long it turn off to achieve the output, the desired output. Okay, the output will also go through the filter and rectify. I think this rectify is a common name. If you already rectify here, then you don't do it here anymore. Okay, it depends on what you want, AC or DC. And the output could be both either mechanical or electrical. Electrical, then, for example, 5 volts is electrical output. If it's mechanical, then it connects to a motor, for example, something that we're dealing with kinetics or mechanical. Then you will have all the sensors, right? Sensors like voltage sensor, it could be current sensor, it could be the speed sensor. For example, the speed sensor, you want to know, is it constant speed or you want to increase the speed, the fan, for example, then everything is sensed and give back to the control circuits. And all these are known as the feedback variables. Okay, these are all the variables. Could be voltage, current, power, what else? Speed, sometimes temperature. You want to control the humidity and temperature of the room. Okay, all these can be feedback into the control signal, and then the circuit will be doing the job to control the switch. So it's called this loop is called the what? Closed loop control. Okay, if you still remember your control subject, you learn about open loop circuit and closed loop circuit. Closed loop and open loop, what is the difference? Open loops, you don't have the feedbacks. It's going through from A to B like that. Closed loop, you have the feedback control, and then the output can be controlled in the desired, required manner. Okay, so let's see what are the types of applications. Okay, just now we talked about static and drive, right? What is static? Static, it doesn't involve any rotation, no kinetics. Okay, no kinetics. Drive, drives. Imagine that you're driving your car. Okay, it's moving, so it contains moving parts or rotating components such as motors. So that is drive. Static, no moving. Drive, rotating. The example of a static converters, we have chapter 1. Not chapter 1. Chapter 1 is just introduction. Let's see here. UPS here, uninterruptible power supply. Power generation and transmission. You see the transmission line, anything moving? No. It's static. Welding, heating, cooling, electronic ballast. Electronic ballast is for the lights, yeah. LED also, you need to have electronic control, yeah, the LED lights. So everything is not moving, not involving any kinetics. So it's called the static. Static. So where do we drive the application? Where do we use the drive? For example, traction, trains, right? Electric trains, electric vehicles. So we call it EV, electric vehicles. Air conditioning, inside the aircon, right, there is a compressor. So that is moving. So involve moving, then conveyor belts, factory automation, anything that involve the kinetics energy is falling under drive category. So if you look at the chapters distribution just now, we start with the static converters, and then at the end of the chapter, we will continue with application of drives. How do we use the static converters to match with the, or to connect to the load, for example, the motors. And then motors, you know that we have DC motors and AC motors. They are not the same. Okay, different drives, AC drive and DC drives will require different power electronic converters. Okay, so this is the diagram showing you the scope and application of power electronics. So you see that it's actually ranging from very low voltage to very high voltage. High. Okay, high voltage is where? High voltage and high current means what? High power. P equals to IV, right? So this area, the red color, high voltage, and also high current, it becomes high power. The green color, medium voltage and medium current, if you multiply, it becomes medium power. Low voltage and low current application, that will be low power application here. Server PC, hard disk, DC-DC converters. Can you tell me one example of power electronics that you've been using it every day?
Mobile phone?
Is it mobile phone?
Yes.
Is there any switch in mobile phone?
Not sure.
A mobile phone, I would say, is an electronic device. I want to have power electronics. Yeah, you're almost there. How do you charge your mobile phone?
Using charging.
Yeah, the charger itself is power electronic. When you charge your mobile phone, right, you plug in your charger to the wall socket, right? The socket is giving you what? AC or DC?
AC.
Okay, this is a socket. Socket come from TNB here in Malaysia Peninsula. TNB supplying AC. So you plug in your socket. How to draw the socket? Okay, something like this. Okay, so this socket will plug into your mobile phone. Mobile phone is DC or AC inside the battery?
DC.
Battery is DC. So what is the game here? DNB give you AC. You need to charge your battery, which is DC. I need to change from AC to DC, right? So who is doing the job? Your charger. When you charge your mobile phone, this charger actually inside is a rectifier. Inside the charger is rectifier, changing from AC to DC, giving you the output of 5 volt, for example. USB charging your mini USB or the USB-C, charge your mobile phone's battery in about 5 volts. So that is power electronics. This power electronic happens inside the charger itself. That is the one that you always use it every day. But then in laptop, for example, you will have your laptop charger, right? Same thing. Your laptop charger, there's a box here, the laptop charger. And then this is the socket. The plug. The laptop charger is actually the same thing, rectifier. Because inside the laptop it consists of a battery, and battery is DC. And charging from the socket itself is AC, so this is a rectification. Of course, the charger for the laptop will be more complicated because lots of we call it protections required. Okay, laptop is very fragile compared to your mobile phone. And then what else? Okay, you can see the pictures and the wording here. The range of application from low power to medium power until the high power. High power normally refers to the power transmission starting from the power generation or power plant, power stations. And then if we look at the new tractions, dealing with electric tractions, we have the magnetic train today's, right? Magnetic levitation trains require very high power to control the magnetic. So that belongs to high power applications. And EVs in the medium categories, medium powers. And then most of the electronics things that you use today under low power application. So all this requires power electronics, right? And we can go through of them. There's actually a lot, but I'm just go through the scope only. In the industrial, you can use a lot, yeah, because they are dealing with conveyors, automations, motor drives is required because all this requires moving parts. Moving, it falls under drives. Weldings, lighting, all this requires a lot of energy that to control. And transportations, all this you can read. If it requires electrics, then you need to do the control. Otherwise, your train will not stop or will not speed up or will not do whatever job that you want. Utility stamps and applications. This is high voltage HVDC. High voltage DC application is evolving due to in Malaysia we only have HVAC, HVAC with high voltage AC application. But HVDC is actually rising, evolving. China as well. It started from the Scandinavian countries or the North Europe countries. Why? Because they have lots of renewable energy like wind. Okay, basically a lot of wind farms. They're generating lots of renewable energy, PV as well. Okay, so because the countries in the Scandinavians, they have different standards. And so to transport from one country to another requires you different standards and different synchronization. So it's quite difficult. So they do HVDC. Another one is because of the cost. For long transmission, because from one country to one country, right, it's a very long transmission. The DC, HVDC will give you better economics return compared to HVAC. So HVAC is suitable for short to medium transmission. For long transmission, they use HVDC for DC transmission. So HVDC will deal a lot with power electronics, because inside you will need to have rectifications, and then you would have a lot of filters, as well as when you come to the countries in the receiving point, they will need to have inverter to invert back from DC to AC. Why? Because most of the application in local is AC. Why? Our facility already established with DC. So if you go to any countries, also different sockets, different plugs, but the electricity is AC. Okay, it's either 100 volt or 230 to 240 volts. In Malaysia, we have 230 volts. Tesla in China is what? What is the line voltage?
It's 222, but 200, 220.
Or still 220?
Yes, 220.
In US is 110. Okay, so UK is 230 or so. Malaysia, we follow UK standard. So different countries, you have different line voltage, as well as line frequency. In Malaysia, our line frequency is, anyone knows what is the line frequency in Malaysia?
50.
50. 50?
Yeah.
What is the unit?
Yes.
Hertz. In China?
Same, I think, also 50.
You're not sure?
I think so. Yeah, because I've got a long time, long time not coming back.
You should know, right? Even though you're not there.
Yeah. I think it's 50, same, I think.
50, okay. In China is 50, okay. What about in US?
60, I think.
Yes, in US is 110 and 60 hertz. So they have different frequency and different magnitude of voltage. Okay, now what else that we can use? Okay, in the power supplies and electronic components, server, computer, telecommunications, what else? Residential, oh, there are lots. Lightings nowadays, because you have the LED, right? Requires the power electronic controls. And air conditioning. Now you can buy inverter-based air conditioning. Okay, why? Because it is able to save cost. How do you save cost using inverter? You can sense temperature. If no one inside, then you can reduce the spinning. When you reduce the kinetic energy, means you save the electricity. So this all requires control and processing, right? So power electronics will be doing the job. And space technology as well, you see that space, where they get the electricity from, mostly is from the PV, right? So PV is one form of renewable energy, and the most renewable energy, right, requires power electronic. Why? Can you tell me why power electronics is required in most renewable energy application? Nobody. Okay, so PV is receiving the energy from where?
Nature from
Where do you get energy from? The PV is receiving energy from?
solar.
Yeah, the sun.
Sun.
A from UTM logo. Okay, no, it's from the sun. So the sun is not a constant supply, isn't it? If we are receiving it from the earth, right? In the space, maybe not the same, right? The sun is constant there. But the earth is rotating in the 24 hours. You have the daytime and nighttime. So on our point of view on the ground, or the inside the atmosphere, the supply of the sun is not constant. And sometimes you have rainy days, cloudy days. All these aspects make it intermittent. Okay, and then fluctuate. Because of clouds. The clouds move from A to B. Oh, it shades. So you have shadings, so meaning what? No supply, no output. Okay, all these are the nature characteristics of renewable energy. For example, if PV, what about wind? Wind is not blowing all the time, right? At the same speed. It also gives you the same condition. So if you have fluctuating inputs and you want the output to be constant, then you will need these power electronics to do the job. Okay. Example of this PV application. Yeah. BIPV. Anyone knows what is BIPV? Anyone? Anyone? B is. Why so quiet this class? You need to talk. Yeah. I'm not going to penalize you. You say something wrong.
Bipolar.
Bipolar. Nope. What is this? Building. It's building integrated photovoltaic, right? BIPV stands for building integrated photovoltaic. It means that you put the PV as part of your building material. Okay, instead of you putting the tiles on the roof, or you put PV on your rooftop. So it becomes BIPV. Okay, what do you need? You need a combiner box, you need data acquisition system to do the control and the monitoring. Because PV is DC, so you need inverter, you need isolation transformer, protection circuits, breakers, and only then you go to the utility, which is the grid. Okay, it's not so straightforward. Yeah, you have a lot of components in between. Okay, what else? In electric vehicles also, electric vehicles, we have many types, right? We have the battery operated electric vehicle. We have a fuel cell operated with electric vehicles. So in most cases, when people say EVs, it's actually battery operated electric vehicles. So we have hybrid types and also have full EV. Yeah? Full EV means that you will have the onboard charger. You can charge the battery. The battery is large, and battery is DC, right? And in most cases, the motor that propel the wheel is AC. They are using the induction motor. Most cases, they are using induction motor, which is AC. Battery is DC. So DC, how to propel the AC? Cannot. You need power electronics. And what is the power electronic name you need? Inverter. Okay, the inverter will be doing the controlling job. When you press the pedal of the car, means what? You want to speed up or you want to brake? Either case, like if you press the petrol pedal, then it's accelerating or speed up. If you press the brake, it will brake, isn't it? So all this information will be given to the power electronics as a signal to control the motor, to propel the wheel of the car, electric cars. Okay, there are a lot more in wind. As I said just now, in power electronics, cannot run away from RE. RE stands for renewable energy. In most renewable energy, because of their nature characteristic, power electronic is required. So if you look at the nacelle, this is called the nacelle of the three-blade vertical axis. This is horizontal axis. Horizontal axis wind turbine. Inside here, where is the power converters? Not so clear. I think it's not here. This is the generator, so the power converters will be underneath, maybe, or it's not shown in the picture here. Okay, here is clear. Do we have? Okay, not mentioned also. Power electronic converters normally is after the generator. This G is generator. After the generator, you will have the power electronic converters. AC to AC or maybe AC to DC, depends. Okay, the box that I just draw here is the symbol that we use to represent the power electronic converters. Yeah, this is cycle converter, and this is rectifier. More examples, you can look at the pictures here. Okay, is it important to study power electronics? Well, it depends. You can see that the graph showing here. What is this? That is the power devices market. Why is it improving or not increasing? On the breakdown of MOSFET, IGBT, thyristors, we're going to study this all, yeah. Why is it increasing? Because of the RE, thanks to the RE as well as all the electronic devices, the modern electronic devices that you're using today. Those requires power electronics. So if they are expanding, so power electronics is going to accompany together. Because the gadgets that you're using, they're not going to last forever, right? It needs to be charged. So when you need to charge them, you need power electronics. The semiconductor device is required. And you know that most electronic components, they have their life, right? They're not going to sustain for forever. Normally, the electronic devices, their life is about 5 years. But thanks to you guys, you change your mobile phone every year, I'm not sure, then the life becomes shorter and shorter. Because new model of electronic gadgets come up every year. So if you change, for example, the Apple products, Xiaomi, etc. Okay, so it's increasing, yeah, because of the trend of power electronics. So we need to know when you say that the trend of power electronics increasing, the types of control circuit also improving from time to time. Why? Because we need to have a better output. What do you mean by better output? Okay, when you buy a mobile phone today's, right, we're talking about the charger, 33 watt, a watt. And then it goes, what, 66, is it? I'm not sure the number, about 30, 60 watt charging. Quick charge, we call it quick charge. Which one do you like? You want the low power charge or you want the high power charge? We want the fast charging, isn't it? We talk about EV, right? EV, you need to charge your car for 1 hour before you can drive. You want to drive that? No. You want to charge it in maybe 10 minutes. You can full charge your car. That is a super quick charger. What is that, super quick charger or quick charger? They are power electronics. Okay. So better output is increasing from year to year. So different material or different devices will be used, okay? Because the frequency of the device that it can control may also change. The power that use it in the devices also may increase. Okay, what is the objective of power electronic circuits? Basically, is the same with the definition here, is to match the voltage and the current requirement to the load. So what is the objective of the electric car? To propel, right? So who is doing the work? The power electronics, which is in this case, inverter. Inverter is one type of power electronics. Okay, to achieve the objective of the load, it will do the control based on the feedbacks. And what does it controls? Either one, voltage or current, or both voltage and current. They call it as control variable. Okay, so the supply would be the battery. This is the VS, or we call it the supply. That would be the power electronics, which is the control. And the load, where is the load? The propelling of the wheel. Okay. So when we say to match the current and voltage, it could be any forms. Just now we said that power conversion or energy conversion, AC and DC. It could be either one or both. Okay, you can change from AC to DC in terms of voltage and current. This is changing form of AC and DC. Yeah? You can change from AC to DC, DC to DC, AC to DC. either forms. Okay, and then you can change the voltage magnitude, yeah, from 5 volt to 12 volt, for example, from 230 volt to 110 volt because of different countries. That is called magnitude. You can change the phase angle as well, for single phase and three phase. The angle, the phase. You can change the frequency. In Malaysia, 50 hertz, matching to US 60 hertz. Not the same. You can change it using power conversion or power electronic devices. Okay, what else? Waveforms. Sometimes you have distortion. Yeah, the sine wave is not beautiful. You have this kind of distortion. This is called harmonics. So in layman, people will say it as noise. Okay, this noise can be compensated. Okay, to be improved, make it beautified. You can beautify the signal using power electronic conversion. Okay, what else? Okay, all right. We have types of power electronics. If you're changing from AC to DC, it's called rectification. The name of the converter is rectifier. How to draw the symbol of rectifier? Just draw a square box, divide by two triangles, and AC to DC. What is the symbol for AC? This one. DC, this one. Or if you don't like one line, you can draw two lines, this one and this one. So you put it in. All right. What about DC to DC? There will be two straight lines. AC, AC, same thing. Sine wave and sine wave. Last one, inverter. Inverter would be changing from DC to AC. So the first half is the input. The second half is referring to the output. So these are all the symbol of the converters. Okay. What's the name of AC, AC? DC, DC, we call it chopper. Chopper is like helicopter, yeah. And AC, AC, we call it cycloconverter. Okay, so in this course, SEEE4433, we are not going to touch this one. Nope, we are going to talk about rectification, inversion, and DC-DC conversion. Okay, power flow, we have unidirectional and bidirectional. What do you mean by uni and bi-directional? Okay, unidirectional means that one way. Okay, you have the supply going to the output in one way. That's all. You're supplying, you're receiving. That's it. What about two ways, or we call it bidirectional? Bidirectional means you have a battery and it's connecting to a load. And this load is able to generate, for example, is EV, right? EV, we can have, when you brake the electric cars, it can have regenerating braking. We call it regen. Regenerating braking is able to produce power. So when you produce power from the EV, actually the power is going back, supplying to the battery. So your EV can charge your battery in this way. Okay, so a little bit. So that is called the reverse or the negative power. Negative power means that you are charging back from the load. Positive power means that it's charging from the source. So when it's charged back from the power of the load, it becomes this way. So either way, charging and discharging is called the bidirectional, two ways. Okay, so that's called the bidirectional converters. This one is called the unidirectional converter. You can only charge the battery. The battery cannot charge back the source. No. Okay, for example, you have a PV, charge the battery. So battery, PV is a source. PV can charge the battery. Can I charge the battery from battery to the PV? Or cannot? Because the PV cannot receive charging, cannot receive electricity. So this is only one way. It's called the unidirectional converters. So the converter, or inside here, the switch and also the control strategy, control techniques used in the unidirectional is much more simpler compared to bidirectional, because bidirectional will not be so easy. It needs to deal with charging and as well as the reverse flow of energy. So bidirectional is more complicated, and the schematic of the circuits also, or we call it the topology of the circuits, also not the same compared to unidirectional. Okay, that's all for the first part. Any question? Right, so welcome back on the second part of the chapter 1 files. We have 4 parts in chapter 1. So this second part is quite lengthy because we have 47 pages here. But I want you guys to go through the content, yeah, because it is useless for me to talk a lot, but then you don't get the info, because most of the material here would be identifying the characteristic of the device. For example, what is thyristor? Thyristor is this one. So what is the characteristic of thyristor? You need to remember, how do I turn on the thyristor and how do I turn off the thyristor? So how do we draw the thyristor symbol? This is the symbol. And what about the expansion of thyristors? We call it as triac. What is the symbol of triac? This one. And then what is IGBT? Where does the IGBT work in the characteristics? And what is the symbol of IGBT? And then in this file, the important thing is you need to identify the device, which is IGBT, MOSFET, etc. These are all the devices. They can work in the range of what? For example, the rating is about 3.3 kilowatts. Kilovolts is referring to low voltage or high voltage? High. 1.2 kilo amps is 1200 amps. Is it low or high? High. So high voltage and high current. Okay. What about the frequency? Can this IGBT work in the high frequency? It doesn't seem to be high frequency here. Here you say that typical application is 20 to 50 kilohertz. Is kilohertz high? It belongs to medium, all right? Because high frequency here we refers to hundreds of kilohertz. Let's see, any example hundreds of kilohertz? If we have MOSFET here, MOSFET already passed. If we have MOSFET, here you are, MOSFET. What is the frequency? Frequency of MOSFET. There you see, frequency of MOSFET is more than 100 kilohertz. So 100 of kilohertz and above, it belongs to the high frequency range. So example in the test, right? We want to do some application that requires high frequency, medium voltage, for example. So who is the candidate? High frequency, there are not many candidates that can operate in high frequency. So one of them would be MOSFET. And the voltage is in the range of medium 500 volt. Just now you see IGBT is working in high voltage, in the kilovolts. So these are all the characteristics of individual devices. So that will be a summary here, summary of all the devices that working in different range of frequency. At the bottom here, you have frequency from low frequency to high frequency, and from low power to high power on the y-axis. So if you can remember this diagram, then you can easily identify which device is actually suitable for which particular of application. Okay, what else? Okay, basically this is the one that we're going to go through. So in this side also, we're going to talk about ideal versus practical. What is ideal? What is practical? Not sure. Later, we're going to talk about it. Okay, let's start with the first slide here. What is the important features in review of practical semiconductor devices. What is semiconductor devices? Semiconductor is a device that operates in between the state of conductor and insulator, right? And in normal conditions, semiconductor is an insulator. It doesn't conduct electricity. But in certain stage or in certain conditions, when it's being triggered, then it becomes a conductor. So we have PN junction here. So the most common semiconductor device that you learn before is diode, right? Diode is made of PN junction. It's called the semiconductor device. Okay, what is the function of this diode? Symbol of diode is a triangle plus a line. Which one is anode? Which one is cathode?
Anode is on the left side, cathode is on the right.
A or B?
A is anode.
Anode.
Yeah.
Plus. B is
Cathode.
cathode, negative. Okay, so the diode function is to allow unidirectional flow of current, isn't it? From anode to cathode. Can I flow the current from B to A? Can I go this way?
No.
No. So it's a off, isn't it?
Yes.
If I go from A to B, it will be on and off. So this is a diode. It allows a single way of flow for the current. When we talk about this graph, we look at this graph, the ideal switching device will be expanding this side. What does it mean by expanding that side? Increase of frequency and increase of power application. We want to have a large power and large high frequency operation. That it should be able to handle high power. For example, that what is this? Wind turbine. Latest today, the latest the new wind turbine, 3-blade wind turbine, right, is about 15 megawatt. How to write megawatt? M for mega, and then W is for watt. Megawatt. 15 megawatt for one single turbine. Is 15 megawatt small? It's very large. Yeah, imagine that how many PV panel that you can put. You need to put how many PV panels equivalent to one this turbine of wind turbine. One PV panel normally is about 300 watt. So you can calculate 15 mega, which is 60 here, divided by 300 watt, one panel. So how many panels do you need to put? How many football fields actually you requires to represent this equivalent? Anyone did calculation? How many?
Around 500
Huh?
kilo.
500 only.
1,000. 50,000.
50,000.
50,000. Oh, how big is that? How large area do you need to put the PV? Cannot imagine. 50,000 of PV. So this one only one wind turbine. So it's actually very, very big and large power. So this one requires power electronic inside. Inside this one is actually called the nacelle. Okay, the box here, the container. Inside you have the brake, you have the generator, you have power electronics, you have transformer, normally at the bottom. So this power electronics switches that you need to have inside this nacelle actually has to handle this 15 megawatt. Is up there. It belongs to high power. And depends on the control strategy that you want to work. Maybe you want to work in the high frequency. Then you have to switch from this side, high power, going to right hand side. Here belongs to what? High power and high frequency, this area. So this graph actually has to expand to that side. Okay. So that is the important features of the semiconductor. It should be able to, because we know that all the semiconductor has its own limitation. Okay, for IGBT just now you say it can only handle 1 point something kilovolt. Okay, for example, 1 kilovolt. Is 1 kilovolt able to be used in this 15 megawatt? We're not sure, depends on the design. So if this IGBT can increase the capability of 1 kilowatt to 10 kilowatt, then it will be able to suit or cater to more high power applications. For IGBT, for example, IGBT normally is used in the inverter. So that is the important features of electronic semiconductor devices. We want to talk about the frequency expanding and also the power handling capabilities. Okay, what is the switching circuit that we're going to reverse back to the basic operation? If you start with this graph on the right hand side here, you see the input voltage. We know that AC, right? AC input voltage. This is AC, AC. No, is it AC? This symbol normally used to represent DC. If AC is like this. Okay, so this is AC input sine wave. We have positive half cycle and negative half cycle. Okay, please, you guys remember we call this positive half cycle, and this is called the negative half cycle. So the middle part is actually pi, and the second part here, the T capital is 2 pi for the duration of. Pi is what? 180 degree. 2 pi? 360 degree. What is T here representing? Period. What is period? Anyone? T equals to 1 over F, which is the frequency. Right. Please remember, yeah, those basic things. The T is 1 cycle, 1 full cycle. You learned that in the second year already. 1 T equals to 1 over F. So you're going to apply all this knowledge in the calculation later. Okay, if you look at the switch here, the switch says what? Let's see. Okay, the switch is open or closed. This is the control function. The switch is on when it travels from 0 to half. Where is 0 to half? This side, right? From 0 to half. Let me name it as A, B, and C. So the switch is on from A to B. And the switch is off from half to T. Half to T is from B to C. Okay. Let's imagine. So the current is flowing from A to B, so it can go through because it's on, right? On means close lah. Off means open. Okay. When it is closed, then what happened to the load? Do we have output? The current is flowing.
Yes.
Yes. So this output will be taking the input. This voltage, the V out, because it's just a pure resistor, so the resistor waveform will follow the input waveform. Okay, resistor is just a constant, so it will follow the input waveform. So you expect this one will be the output. Okay, what about when the switch is open? Open. Can the current flow?
No.
When no current flow means the V out is 0 multiplied with a constant, you get 0, right? So it will be a constant line here, 0. So what do you expect the output would be? The output will look like this one. From A to B, you follows the output follows the input supply because the switch is close. So from B to C, the switch is open, means that the current is not flowing. So you get nothing. Output is 0. So it representing the same behavior as a diode. Diode allows a single directional. So when the current is positive, it will flow. When the current is flowing from here, can it go reverse? Cannot. This is a blocking diode. So there is no output here during the negative half cycle. Okay, so that is the function of a switch. So diode here is working as a switch to make it on and off. How long? When it is on, we call it T on, time for on. When it is off, we call it T off. What is the relationship between T on and T off? If I plus these two, equals to the period, capital T. And capital T equals to 1 over F. So you guys are going to play around with this T on, T off, and F. Okay, you need to know where they stand for. On time, off time, and the period, frequency. For ideal, yeah, that's the word ideal. Ideal, and then with the word of practical. So we have an ideal versus practical. Ideal, normally we say that is no losses. Okay, ideal case doesn't happen. In real life. In real life, you don't have the ideal case. What is your ideal girlfriend or boyfriend? Okay, I want her to be beautiful, not wearing spectacles, very clever. Those are ideals. When you meet a new girlfriend, it doesn't meet all the requirements. So it doesn't happen in real life. Same thing goes to your characteristic of switching here. So what is the ideal component or the characteristics that you use in power electronics? No power limit. In real life, every component has its own limit. Okay, 500 volt is the limit. You cannot go beyond 500 volt. Okay, that is the limit. 0 turn on and turn off times. No switching speed limit and infinite frequency operation. Nope. In real life, you buy a thing, you on and off maybe 1,000 times. Oh, broken. But in ideal case, it doesn't break. It will be able to work infinite times, right? No power dissipation. Dissipation means what? Heat. I'll call it loss. Why is it become very hot, the component, when you turn it on for some times? Because of the dissipation of power. Losses happened, and the losses will be transformed into hot or heat dissipation. Okay, because you have internal resistance and leakage current. But in ideal case, there's no such thing because it's ideal. So ideal, no power limit, there will be no power dissipation. There will be 0 of turn on and turn off times. Everything become very perfect. So that is called the ideal switch. Okay, so when you turn it on, it become on automatically, instantaneously, sharp at 0. 0 is 0. And I want it to turn off at T1. On, off. So off immediately at T1. On again T2. It on immediately T2. There's no need to wait. Okay, that is ideal case. And the symbol that you use to represent ideal switch is something like this. On and off only. Very simple. But in practical, does it goes that way? No. You see that this one, I want it on. I want it off immediately. But in practical, I want you to turn off. Okay, turn off, yeah? Okay, turn off T1. When does it turn off? It turn off at this point because it will go down gradually. Okay, it's just like a slide. It's slide down. And I want it to turn on at T2. Does it happen at T2? No, it happened at this point, steady state. Because from T2 to this point is actually called the transients. Okay, it's called the dynamic response. Dynamic response. Okay, in ideal case just now, do I have the dynamic response? I cannot see because it happened instantaneously. How to spell instantaneously? Okay, whatever. Okay, instantaneously, right away, immediate, no losses. If I multiply the voltage and the current at this time, what do I get? The voltage is high, right? And the current is 0. So current multiplied with voltage, what do you get? 0. There is no power losses. Because either component will become 0 at the time of T1 and T2. So you multiply them, you always 0, the power. Okay, the power is always 0, no losses. But if you go to practical, this T1 and A and this is B. From T1 to A, either way you see the current is going up and the voltage is falling down. This one becomes steady state. So if you multiply current and voltage in this range, you get this curve because the current is there and the voltage is there. So the power is become like this one. Same thing goes to from T2 to B. So this area is actually what? The power that rise up and down because of the losses. Okay. In ideal, there's no losses. In practical, you have this kind of losses. Okay, power losses. Is it okay? So these power losses will do what? It will bring down the efficiency because the power is supposed to be transferred to the output. But because your turn on and turn off is not ideal, you have some lacking here, the power dissipate in terms of heat. It cannot be used in the output. So it will bring down the efficiency of the converter. Okay, so the best is we don't want this to happen. But in practical, we cannot run away. It will happen anyway. What we can do is to bring down the curve as low as possible. So bring down the Pmax, make it smaller looped. Okay. Okay, that is the difference between ideal and practical in terms of diode. If you look at diode, the curve is off, on. But in practical, when you turn on the diode, you have the bias voltage dropped 0.7. Okay, if you still remember, right? Germanium is 0.3 volt, I guess. For diode of silicon is 0.7, if I'm not mistaken. So this 0.3 and 0.7 volt is actually the practical characteristic, the losses. We call it voltage dropped. Okay, the voltage dropped because the operation happened. But in diode of ideal, when it happens or close, there's no voltage drop. Okay, just fine, just go. But here in practical, you want to go, you pay 0.7 volt before you go. So this 0.7 volt is the voltage drop. In real life, that is what's happening. Okay, real diode, you have losses of voltage. And then it depends on what is the current that flows here. The current multiplied with 0.7 become the power loss. Okay, ideal versus practical. Please read. They are all text. What is the keywords here? Let's say zero current flow, but in practical, no, there will be a small current flow. Large current and zero voltage drop, or no, it doesn't happen. There will be a voltage drop in real life. Switch from on and off instantaneously. Okay, spelling of instantaneously. But no, in practical, it will come gradual or exponential. It takes some times to turn on and to turn off. Ideal, very small power required. Okay. Do you need power to turn on the device? But in ideal case, small power. But in practical, it depends on what do you choose. IGBT, MOSFET, GTO, they all have the requirement. For example, like you want to power your IC, integrated circuit. You need to feed the power to the integrated circuit, right? You have positive VCC and negative VCC, right? Because it needs to operate. Same thing goes to IGBT, MOSFET, and GTO, etc. It requires small power or different requirement of voltage and current to turn on and to turn off. Good. That is the requirement in practical versus ideal. They are not the same. But the switch operation is to turn on and turn off. Okay, still the same. But the behavior is not the same. Okay, before we finish the class today, we stop here. What is uncontrolled, semi-controlled, and fully controlled? Please remember, diode, you cannot do the control because it only allows one way. And there's no way to control the diode. Thyristor, a new name here, I guess. SCI is the short form for thyristor. It belongs to semi-control. Why is it called semi-control? We'll look at it later. And fully control is the family of MOSFET, IGBT, GTO, all of this. Basically, all of them, it becomes falling under the category of fully control. So we have only 3 of this, 1, 2, 3. Please remember them. Okay, that's all for today. See you again on Thursday. Anything you want to ask?